Welcome back to The Explainer. Today, we're diving into some absolutely massive AI news. We're unpacking a groundbreaking May 2026 archive paper by researchers Fahd Sadiq and Fatama Ferd called Formalizing Latent Thoughts. And honestly, this paper is a total game changer. It exposes a fundamental structural flaw in how our large language models actually think.
Okay, let's dive right into this. We've got a lot of complex architecture to cover, so here's our roadmap: the benchmark illusion, decoding latent thoughts, the 4 axioms, auditing the AI mind, the structural bottleneck, and finally, upgrading your AI pipeline. Just a little cognitive safety net for the journey ahead.
So, I want to kick things off by posing this pretty provocative question to you. Does your AI actually reason, or does it just guess really, really well? Think about how we currently test these models. It's kind of like trying to give a patient a serious medical diagnosis by merely checking their temperature, right? If they pass a benchmark test, well, they look healthy on the outside. But checking their temperature doesn't actually tell us a single thing about what's happening underneath the surface in their internal architecture.
Section 1. The benchmark illusion. For a long time now, high benchmark accuracy has been the absolute gold standard. But relying on these final evaluation pipelines is actually a wildly misleading signal. Under the current evaluation method, we just measure output tokens. If an AI fails a test, the signal is totally ambiguous. We literally don't know if its internal reasoning was flawed or if the final processing layer just didn't have the capacity to output the right words. It completely conflates representation quality with model capacity. But this new axiomatic framework changes all of that. It measures the internal latent representations completely independent of that downstream accuracy. We're shifting from just evaluating what the AI says to essentially taking a full MRI scan of what it internally represents.
Section 2. Decoding latent thoughts.
So if we're throwing out those final output words, how do we actually bypass them to see the thoughts themselves? Well, we look at latent representations. These are the hidden internal states a model produces during inference. This new framework operates directly on these hidden states to force a direct assessment of what the model actually stores. And it bypasses task-specific labels or output tokens entirely. This means it's a completely architecture-agnostic approach. Section 3. The 4 axioms. This is where the paper's framework really gets its teeth. The researchers laid out 4 distinct functional rules for a healthy thought representation: causality, minimality, separability, and stability. And what's so powerful here is that every single one of these axioms maps to a measurable quantitative property of the latent space, without ever touching the loss function. Let's break these down real quick.
First up is causality. This just means the representation has to link directly to downstream behavior. Basically, if you change the latent state, the output distribution has to shift predictably. This is crucial because it filters out representations that are structurally inert, or essentially just dead space that's become completely decoupled from the generation process.
Next is minimality. A healthy thought representation contains only the information strictly necessary for the task, because if a latent state is flooded with redundant or noisy signals, it severely dilutes the reasoning capacity and puts a massive, unnecessary amount of pressure on the context window.
Third, we have separability. This one is absolutely critical. The representation must distinguish between distinct queries using geometric distance. Think of it like a giant corporate mailroom. If 2 entirely different questions within the same department get sorted into the exact same overlapping bins, the model simply can't route them to different reasoning paths. Without that geometric distance, reasoning just collapses.
Finally, stability. The internal representation has to remain consistent even across minor input perturbations, like adding a bit of token-level noise or just paraphrasing the prompt. If the latent state collapses just because you asked the exact same question in a slightly different way, downstream reasoning becomes dangerously non-deterministic.
Section 4. Auditing the AI mind. Okay, this is the climax of the explainer. The researchers didn't just propose these axioms theoretically, they ran a massive audit of modern open-weight LLMs. And the scope was incredible. They didn't just look at one niche model. They evaluated them across 23 different reasoning tasks, including highly complex spatial reasoning and factual QA. Plus, they comprehensively spanned dense architectures, reasoning distilled models, and even RL-trained model families.
And what did they find? Well, I'm just going to read this exact quote from the paper. No candidate satisfies all 4 axioms simultaneously. Let that sink in. That is an absolute structural failure. present across all modern LLM architectures they tested. Every single model failed at least one fundamental axiom. So the crucial point is zero models pass the representational integrity test, which unequivocally proves that our current training objectives are fundamentally misaligned. We've been optimizing these models to pass multiple choice tests without ever making sure the actual geometric architecture holding their thoughts works properly. Section 5, the structural bottleneck. Based on their deep dive into the latent geometry, the researchers pinpointed exactly where the models break down. Models actually succeed at task-level separation. They reliably separate a spatial reasoning task from a factual QA task with a high margin. But look at the failure in query-level separation. If you ask the model two different questions within the exact same task, those internal representations collapse into similar, non-separable states. The model literally cannot structurally distinguish between two different questions in the same domain. And it gets wilder. The audit revealed that latent states encode almost no new information beyond the initial input embeddings. So what does that actually mean? Well, it means shoving more tokens into a context window is going to yield massive diminishing returns. The AI isn't actually enriching the representation as it computes. Almost all the signal is just sitting exactly where it started at the input layer.
Section 6, upgrading your AI pipeline.
These revelations demand a major shift in how we build. For developers, here are the actionable takeaways. First, you have to start auditing your latent space independently of standard benchmarks. Second, use those 4 axioms as CI/CD pre-checks. Monitor the information entropy delta between your input embeddings and your final hidden states. Implement these axiomatic metrics right into your internal scoring systems. And finally, because these models cannot separate queries internally, you must rely less on latent routing and much more on explicit structural prompts. Remember, this is a structural gap, so just throwing more compute or larger data sets at the problem won't fix a thing. Which leaves us with this final provocative question to ponder. If scaling up data and compute won't fix this fundamental reasoning gap, what architecture will you build next? It's time to rethink the limits of transformers and demand that our AI systems actually construct healthy thoughts. Thanks for exploring this complex topic with me, and I'll catch you on the next explainer.